Let's meet Tom and Kate. They are financial analysts in a business company, and they need to exploit HPC applications for complex stock option analysis. During their everyday work, they rely on the HPC cluster the company owns to fulfill their jobs. One day, while Tom was working, his boss came to his office and asked for a financial analysis for a customer that must be completed within 3 hours. Tom started to work on it immediately. He configured the application with the customer specifications and submitted the job to the cluster. The cluster was lightly loaded and the analysis ended in 2 hours. The deadline was met and both Tom and his boss were satisfied. The same day, the boss asked both Tom and Kate two financial analyses setting two different completion times of 1 and 3 hours. They submitted the jobs, but unfortunately this time the cluster was heavily loaded and one of the two deadlines was missed. In this scenario, we are facing computationally intensive workloads which are well suited for heterogeneous hardware acceleration, but usually generate high contention on resources. This is especially true when the workload can't be predicted. We need something to orchestrate the execution of the applications. RHetOS is our solution. RHetOS allows applications to express performance goals and constantly monitors their behavior. With these informations, it automatically orchestrates the execution of applications on heterogeneous hardware, and as a result, RHetOS mitigates the slowdowns on multi-programmed workloads. The architecture of the system is immediate to understand. We have a set of running jobs for which the programmer provides different implementations for different hardware resources. The user can specify a performance goal for each of them. These resources can be general-purpose processors, graphic processors, or reconfigurable devices, and they can be present in different numbers and combinations. The system relies on constant monitoring of application performance. The collected data is used by decision policies to take actions on how to share resources in the system. The system relies on an ODA loop with the goal to realize a self-adaptive system capable of adapting at runtime to changes like the arrival of new applications or the failure of some nodes in the system. Let's see how it works. The application designer instruments the application. We provide a set of easy-to-use APIs that are used to communicate to the system that a given computational kernel can be executed on multiple hardware devices. At the same time, the system exposes useful and simple APIs to create a monitor and expresses the performance goal. Finally, in the hot loop of the application, the designer asks the system to execute a given computational kernel and communicates the system the progresses. Let's have a look at some examples. With RHetOS, we are able to enforce a certain performance level. For instance, if we run one application only on the GPU, we run at very high performance. However, if we run it solely on the CPU, we obtain a lower throughput. If the final user is interested only in finishing the computational kernel before a given deadline, this translates into executing at a given fixed throughput. With RHetOS, we are able to control the execution to fulfill that user goal. In the same way, if we have different applications, the system is able to allocate the resources to each of them, trying to respect the performance goals they specified. With RHetOS, if the boss asks Tom and Kate two analyses with two deadlines, the outcome will be different than before. They submit the jobs to the cluster, and then the RHetOS system takes care of respecting the goals specified by the users, automatically managing resource assignment to mitigate slowdowns.